Hi, and welcome back to Chapter 1, Electric Charge and Electric Field. This video presentation will serve as a supplement to the 3 modules of this chapter. In this video, more examples of electric force and electric field calculations will be discussed and analyzed. Our first example is an electric field calculation. We have 2-point charges, as shown in this figure. We are then asked to find the magnitude and direction of the total electric fields at points P and Q. For the first problem, the electric field at point P will be due to the charges Q1 and Q2. At point P, the field due to Q1, which is E1P, is directed towards Q1 or downwards since it's negative. Similarly, the electric field, due to Q2 at point P, is directed away from Q2. In this case, E2P is in quadrant 1. The total electric field vector at point P, EP, will then be a superposition of these two vector fields. In terms of components, the vector EP is shown as these. E1P only has a negative y component, while E2P has both positive x and y components. We first solve for the electric field due to Q1. Before we apply Coulomb's law for electric fields, we first need the distance from Q1 to point P, R1P. In this case, R1P is 2 meters. Using these in the value of Q1, we can then solve for the magnitude of E1P and get a value of 2.25 newtons per coulomb. We next solve for the electric field due to Q2 at point P. But first, we need the distance or 2P in the direction theta 2P, which is represented by this right triangle. We solve for our 2P squared first using the Pythagorean theorem to get 13 square meters. We then use this value to solve for the magnitude of E2P and get a value of 0.69 newtons per coulomb. Let's go back to the right triangle in the figure. The direction of the field vector, theta 2P, can be obtained using the tangent inverse of the opposite side length over the adjacent side length of the right triangle. This gives us a value of 33.7 degrees. Knowing the magnitude and direction of E2P, we can solve for its components using cosine and sine laws. We then obtain a value of 0.57 newtons per coulomb for E2Px, and 0.38 newtons per coulomb for E2Py. Substituting the obtained component values to the equation for EP, we now have solved the total electric field vector at point P. We have to take note that this vector has a positive x component and a negative y component, implying that this vector lies in quadrant 4. We then use the Pythagorean theorem again to solve for the magnitude of this vector and obtain a value of 1.95 newtons per coulomb. For the direction, we obtain a value of negative 73 degrees or 287 degrees in standard angle measurement. Let us proceed to the second problem, the field at point Q. Since Q lies along the line connecting Q1 and Q2, then the problem is just one-dimensional. The field due to Q1 at point Q is still towards Q1. In this case, E1Q is directed towards the positive x-axis. Similarly, the direction of the field due to Q2 at point Q is away from Q2 or towards the positive x-axis. The total field at point Q will then be the superposition of E1Q and E2Q. Since the two field vectors have the same direction, then their sum will be composed of the sum of their magnitudes. We then again use Coulomb's law for electric fields to solve for the magnitude of E1Q. Using the given values and recognizing that the distance from Q1 to point Q, R1Q is 1 meter, we obtain a magnitude of 9 newtons per coulomb. We do the same for E2Q to get 2.25 newtons per coulomb. Note that the distance from Q2 to point Q is 2 meters. We can then finally solve for the total electric field vector at point P as 11.25 newtons per coulomb I hat. If the final vector is only composed of a single component, such as what we have obtained here, then this can serve as our final answer for the magnitude and direction. Note that it is evident that the magnitude is 11.25 newtons per coulomb, and the direction is I hat, or towards the positive x-axis, or to the right. Knowing the magnitude and direction of the total field at point P and Q, we can verify our results using the Phys simulation called charges and fields. You can view this simulation in the attached assignment resources for this chapter or at the Phys website. Precisely for this problem, you only need to tick the values in grid boxes. In this simulation, the 1 meter length is defined by the legend at the bottom. You then place the charges at the precise location as in the problem. In this case, we only need the 2 charges to have a distance of 3 meters. Point P is located 2 meters directly above the negative charge. In contrast, point Q is 1 meter to the left of the negative charge. In this Phys simulation, we place the sensors at the location of the points where we want to measure the field. At these points, we obtain values close to what we have obtained in our calculations. Note that the values that you will obtain will have errors depending on your placement of the charges and the sensors. The simulation, however, provides a way to verify and check your obtained directions and calculated magnitudes. Let's now have an example of electric force calculation by placing a charge Q3 at point Q. What is now the magnitude and direction of the total force on Q3? For this example, we will present 2 solutions, the methods used in Module 1.2 and Module 1.3, respectively. The first solution will be using Coulomb's law for force. The force exerted by Q1 on Q3, F13, will be directed to the right. Similarly, Q2 will push Q3 to the right. The total force on Q3 will be the superposition of these 2 forces. Since the 2 forces have the same direction, the total force magnitude will be the sum of the component magnitudes. Using Coulomb's law, the magnitude of the force exerted by Q1 on Q3 is then 9 times 10 to the negative 9 newtons or 9 nanonewtons. F23, on the other hand, will have a magnitude of 2.25 nanonewtons. The total force on Q3 will then be 1.125 times 10 to the negative 8 or 11.25 nanonewtons I hat. The magnitude is then 1.125 times 10 to the negative 8 newtons, and the direction is to the right. Since we already know the total electric field at point Q where the charge Q3 is located, we can also use it to solve for the total force on Q3. This force is just the product of Q3 and EQ. Utilizing the previous result, we get a value similar to what we have obtained in the previous method.